I am Tomonari Sei, and today's topic is geometric properties of textile plot. And this work is joint work with Dr. Ushio Tanaka. The textile plot proposed by Kumasaka and Shibata is a method for data visualization. And the method transforms a data matrix X into another matrix Y in order to draw a parallel coordinate plot. The parallel coordinate plot is a standard two-dimensional graphical tool for visualizing high-dimensional data at a glance. And in this talk, we investigate a set of matrices induced by the textile plot, and which we call the textile set from a differential geometrical point of view. And it is shown that the textile set is written as the union of two manifolds if data matrix generic. So first of all, this talk is not related to Bayesian statistics, so I am sorry. And this is the outline of our talk. First, I'd like to explain what is the textile plot. This figure shows an example of the output of the textile plot. This shows the Fisher's iris data, which is very famous in statistics. And it consists of 150 cases of iris data with 5 attributes: species, petal length, petal width, and so on. 5 attributes. And each attribute is transformed by a location scale transformation variate by wise. And in this method, I will explain the next slide, allows categorical data. So there are categorical variate here. And the missing data is also admitted. And the order of axes can be maintained. So let us recall the method of the textile plot. For simplicity, we assume no categorical variate and no missing value here. Let the, X be the data matrix, matrix with n times p elements. And without loss of generality, we assume the sample mean and sample variance of each xj are 0 and 1 respectively. Then in this method, the data is transformed into another matrix y, where each column vector is written as aj plus bj xj, and the coefficients aj and bj are determined by the following procedure. The coefficients a and b are the solution of the following minimization problem. This minimization problem is understood. The intuition of this problem is to determine these coefficients in such a way that the parallel coordinate plot becomes as horizontal as possible. And the solution of this minimization problem is A equals 0 and B is the eigenvector corresponding to the maximum eigenvalue of the covariance matrix of the original data X. Here is a simulated example. Let X be one matrix with 100 times 4 elements. And each row is distributed according to the multivariate normal distribution with this correlation matrix. And the left figure shows the parallel coordinate plot of the raw data X. So 4 columns with 100 lines. And the right figure shows the output of the textile plot. And the difference is because the second variate has negative correlation with other variate. So here is some crossing, but in the right figure, it is more horizontal. And also, if the fourth variate is not so correlated with other variate, so in such case, the data becomes more concentrated. Okay, the textile plot transforms the data matrix X into Y anyway. So denote the map by Y equals tau X, tau of X. And our problem is, what is the image of this map? And by elementary calculation, we can show that the matrix Y satisfies the following two conditions, this one and this one. The first one corresponds to the eigenvalue problem, and the second one is just normalizing condition. And these two conditions motivate the following definition of the textile set. The textile set is defined by the set of matrix of n by p, which satisfies in such that there exists lambda such that for any I, this equation satisfied, and the normalizing condition is also satisfied. And we also introduce the unnormalized textile set, which this is just this is the same except the last condition. And we are interested in mathematical properties of these sets, TNP and UNP. And bad news is statistical implication of this work is not yet, and it is a future work. Anyway, let us begin with a small p case, small dimensional case. For p equal 1, the answer is very simple. Tn1 is the unit sphere. And if p equal 2, the Tn2 is decomposed into two manifolds, each of which is diffeomorphic to the direct product of two spheres. And their intersection, A cap B, is diffeomorphic to the Stiefel manifold with lower dimension. And see next slide for n equal p equal 2 case. And T22 is in R4 is the union of two tori glued along O2, also orthogonal group. It is not easy to imagine, but anyway, there are two tori, and blue line and red line are glued to each other. This is an image of the set T of 2, 2. Okay. And to state our main result, our main result is about for general dimensional case. To state our main result, we define two concepts. One is the non-compact Stiefel manifold, and the second one is canonical form. Let n is greater than or equal to p, denote by B star the set of all column full rank matrices. Rank Y is P. And this is called the non-compact Stiefel manifold. And the dimension of this manifold is NP, and its closure is the whole space. And the orthogonal group naturally acts on V star, just multiply orthogonal matrix from the left. And by the Gram-Schmidt orthonormalization, the quotient space of this the non-compact Stiefel manifold is identified with upper triangular matrices with positive diagonals. So we introduce a terminology. Let us denote by V double star the set of all matrices written as this form, upper triangular matrix with positive diagonal elements. We call it canonical form. And note that V double star is contained in V star, and the quotient space is identified with VW star. And okay, so we restrict the set UNP. UNP was the non-normalized, unnormalized textile set to V star and V double star by these. And the group ON also acts on UNP star, and the quotient space is identified with UNP star star. So it is essential to study UNP double star. Okay, let us check small dimensional case. If n equal p equal 1, it is a trivial set, and if n equal p equal 2, then the matrix Y is written as this, and the set U2 star is decomposed into two manifolds. One is a plane, and another one is a cone. Now we state our main theorem. The differential geometrical property of UNP double star is given as follows. UNP double star is decomposed into two differential manifolds, and the dimensions of which are given by these formulas. So dimension of M1 is this. So codimension is P minus 1, and codimension of M2 is P. And M2 is connected, but M1 may not be connected. Okay, this is a figure of three-dimensional case. U33 double star is the union of four-dimensional and three-dimensional manifolds, so it is not easy to visualize. So we look at a cross-section with two diagonal components are restricted to one, then we have this kind of figure. So and this consists of surface, something like this surface and a vertical line here. So they are two manifolds. Okay, and this is easy consequence. The UNP star, UNP restricted to non-compact Stiefel manifold is decomposed into like this. And for the rest, we state other results. First, we have n equal 1 case, only one observation. If n equal 1, then the textile set is the union of a p minus 2-dimensional manifold and some isolated points. For example, U13 consists of a circle and 14 isolated points. It is a little strange result. And as a final topic, we focus on the differential geometrical characterization of F lambda inverse 0. The map F lambda is defined by this one. These p plus 1 equations correspond to the definition of the textile set. So we have a classification of TNP, namely the textile set TNP is written as the disjoint union of F lambda inverse 0. And we want to know each set F lambda inverse 0. Then we have the following theorem. F lambda inverse 0 is a regular submanifold of the whole space with codimension p plus 1 whenever these kinds of conditions. I'd like to summarize our talk. We defined the textile set and find its geometric properties. Namely, the textile set is decomposed into two regular manifolds. And the present and future study follows. Characterize the classification with induced Riemannian metric from Riemannian geometry, geodesic and curvature, and so on. And the second one, to investigate differential geometrical and topological properties. And finally, can one find statistical implications such as the sample distribution theory and so on? That's all. Thank you very much. Merci beaucoup. Compute.
Yes. For the example that you mentioned that there is a manifold plus 14
yeah.
How you can find them if you have?
Actually, we have more explicit representation of the manifolds. in the proceedings, you can find some formulas. It is written as rational functions and square root and so on. Thank you.
There are no other questions? You can, thanks to the speaker again.
Thank you very much.